Experiment No.6. Frequency demodulation. Objectives: to study the principle of phase-locked loop, to understand the characteristics of PLL LM565 to demodulate FM signalosingpol, to demodulate FM signalosing FMTO aim conversion discriminator. Equipment required: DMM oscilloscope function generator, dual channel, breadboard DC power supply plus 5V, fixed, -5V, fixed, resistors, 100 ohms quantity equals 1, 200 ohms quantity equals 1, 1K ohms quantity equals 1, 2K ohms quantity equals 1, 4.7K ohms quantity equals 1, 2K ohms quantity equals 1. Capacitors 560 pF quantity equals 2, 0.01 UF quantity equals 1, 0.05 UF quantity equals 1, 0.1 UF quantity equals 2, diode, 1N4007 quantity equals 1, IC LM318 quantity equals 1, connecting wires F moduli of experiment No.5, figure 5.3. Theory: frequency demodulator, also called frequency discriminator, is a circuit which converts instantaneous frequency variations to linear voltage changes. There are many types of circuits in communication systems such as FMTO aim conversion balanced and phase shift discriminators and phase locked loop, PLL, frequency demodulator. In this experiment we will introduce the operations of PLL frequency demodulator and FMTO aim conversion discriminator. The operation theory of phase-locked loop, PLL. The PLL is an electronic feedback control system as illustrated with a block diagram. In figure 6.1 of locking the output and input signals in good agreements in both frequency and phase. In radio communication, if a carrier frequency drifts to eta transmission, the PLL receiver circuit will track the carrier frequency automatically. Figure 6.1 block diagram of phase-locked loop. The PLL in this experiment is used in two different ways. As a demodulator, where it is said to follow phase or frequency modulation. Point 2. To track a carrier signal which may vary in frequency with time. In general, a PLL circuit includes the following sections: A. Phase detector, PD, B. Low pass filter, LPF, C. Voltage controlled oscillator. VCO, the phase detector within the PLL locks at east two inputs and develops an output that is if these two input frequencies are identical. If that two input frequencies are not identical, then the output of detector when passed through a low pass filter removing the components is at level applied to the VCO input. This action closes the feedback loops and set the level applied to the VCO input changes the VC output frequency to make it exactly match the input frequency. If the VC output frequency equals the input frequency, the PLL has achieved lock and the control voltage will be zero for as long as the PLL input frequency remains constant. The parameters of PLL shown in figure 6.1 are as follows: KD equals phase detector gain in volt/radian, Ka equals amplifier gain in volt/volt, KO equals VCO gaining Hertz/volt, KL equals KD Ka. KO equals closed loop gaining Hertz/volt. Basic characteristics of LM565 PLL. The LM565 is a general purpose phase-locked loop and is widely used in frequency demodulation. In designing with the LM565, the important parameters of interest are as follows: I. Free running frequency, FO. Figure 6.2 shows simple circuit with LM565. In the absence of the input signal, the output frequency of TEVCO is called as free running frequency, FO. In the PLL circuit of figure 6.2, the free running frequency of LM565 is determined with timing components C2 and VR1 and can be found by F or E running frequency, F equals Hertz, 6.1. KL equals KD Ka. KO equals 6.2. Closed loop gain, where equals total supply voltage at the circuit equals VCC, VCC equals -5V equals 10V. Figure 6.2 LM565 phase locked loop, PLL. 2. Lock range. Initially the placinal ready lockstaten of cois running gets a frequency. If the input frequency, phi, is away from VC off frequency, FO, locking may still occur. When the input frequency reaches a specific frequency where PLL lock. The frequency difference off beyond FO is called the lock range of T. Look. The lock range of LM565 can be found by FL equals Hz, 6.3. 3. Capture range. Initially the lupus in locket and VC is running gets a frequency. If input frequency, phi, is closer to the VC off frequency, FO, unlocking may maintain. When the input frequency reaches a specific frequency where FPL locks, the frequency difference off beyond was known as the capture range of T. Look. The capture range of LM565 can be found by FC equals square root Hz, 6.4. Figure 6.3 illustration of lock and capture ranges. Frequency demodulator based in LM565 PLL. The PLL circuit of figure 6.2 can be used as a frequency demodulator. When the input signal increase in frequency, the output signal decrease in voltage. Inversely, if the input signal decrease in frequency, the output signal will increase in voltage. The Ka circuit of LM565 is equivalent to the of LM566. The free running frequency FOVT. VC is determined with the use of external components C2 and VR1. The internal resistor 3.6 k ohms, pin 7, and the external capacitor C3 form a low-pass filter. The capacitor C4 connected between pin 7 and 8 is a frequency compensation capacitor. FM to AM conversion discriminator. Figure 6.4 shows the blocks of FM to AM discriminator. The input FM signal is first converted into AM signal by the differentiator, and then the output AM signal is demodulated by the envelope detector to recover the original audio signal. Figure 6.4 The block diagram of FM to AM frequency discriminator. In figure 6.4, if input signal is equals 2 plus 2 indefinite integral 6.5, then the differentiator output will be equals 2 plus sin plus 180 6.6. The amplitude of signal varies with the variation of amplitude. Thus the signal is an amplitude demodulated signal. If the AM signal passes through an envelope detector, the audio signal will be recovered. The circuit of figure 6.5 is a frequency discriminator with FM to AM conversion technique. The components U1, C1, C2, R1 and R2 operate as a differentiator. The inverting amplifier U2 with a gain of R4/R3. And the AM peak detector includes 1 R5, R6, C4 and C5. The coupling capacitor C6 is set to blocked level. Figure 6.5 FM to AM frequency conversion discriminator circuit accepting various frequency demodulators mentioned above. L-band pass filters are popularly available in the frequency demodulation in ultra-high and microwave frequency ranges. Figure 6.6 shows the responsive band pass filter. The linear portion on the curve where the voltage A variation is proportional to the frequency variation meets the requirement of a discriminator. Figure 6.6 The frequency responsive band pass filter. Procedure FM to AM frequency discriminator. A. Construct the circuit of figure 6.5 on the breadboard. B. Construct the circuit of figure 5.3, frequency modulator, also on the breadboard. C. Connect plus 3V, DC, power supply to the DC bias input. Apply a sine wave, AC, signal of 2 Vp amplitude and 3 kHz frequency to the audio input terminal of frequency modulator. Adjust the potentiometer, VR1, until a sine wave appears at the output. D. Connect the output of FM modulator, figure 5.3, to the input of FM to AM discriminator circuit, figure 6.5. E. Using the oscilloscope observe and record the input and output waveforms of frequency demodulator in figure 6.7. Figure 6.7 F. Measure and record the frequency of the frequency demodulate output audio signal. FO, measured, equals G. Repeat steps for input audio frequency of 5 kHz. Using the oscilloscope observe and Record the input and output waveforms of frequency demodulator in Figure 6.8. Figure 6.8 H. Measure and record the frequency of the frequency demodulate output audio signal.fo, measured, equals I. Repeat steps ptod for input audio frequency of 8 kHz. Using the oscilloscope observe and record the input and output waveforms of frequency demodulator in Figure 6.9. Figure 6.9 J. Measure and record the frequency of the frequency demodulate output audio signal.fo, measured, equals